Hello, we're Group 28. My name is Shihan Wang with my colleague Shixiong Wang. And our topic is about learning approach for query planning on spatial temporal IoT data. Table of contents of today's presentation is first of all, I will introduce the background and the current state of art, and then my colleague Shixiong will explain the learning approach, which includes feature extraction, evaluation metrics, and experiment results. So IoT data significantly increased in recent years. And this data always associated with the spatial temporal context. Therefore, the query processing engine for this data needs to support spatial temporal computation. And however, the current standard query language for this kind of data does not support spatial temporal query pattern on semantic data. So to be able to get more benefit from this data, it is important to solve this kind of problem. There are several current of state of art. The first one is abstract syntax tree. It is a kind of query parser to translate the given spatial temporal query into an abstract syntax tree. Then the tree is mapped to the internal query operators, resulting a query plan tree. However, this query performance and optimization does not good enough for large number of query. Therefore, some researcher try to find a solution. They use a distributed solution, which is a middleware to integrate several database system, and this middleware is will break the input query into a few of subqueries and separate them to the proper databases. And by using this way, it is possible to dealing with a large number of data. However, it is important to execute the order. However, generating an optimized execution order only based on a selective estimation module without taking the environment performance into account. So therefore, it may result some a high risk of incorrect result. And therefore, some researchers try to use machine learning to predict the query performance, since machine learning is good at deal with complex model, and it is often easier to adapt and use new configuration and data patterns. So there are three kind of approach. The first one is predict the query execution time and the size of results by comparing the similarity of query execution plan. The second one is use machine learning to estimate the percentage of work and produce an abstract number that is intended to present a relative query optimizer's cost. The last one is to predict the SparkQL query execution time. It is claimed that the training time is reduced significantly by using this approach. However, it's mainly focused on semantic data, so have inaccurate results for spatial temporal data. And then my colleague Shixing will explain the learning approach.
Okay, so this figure shows the learning approach overall. First, we got the training dataset comes into the feature extraction. In this phase, we judge whether the query are similar or not. So next we comes to the model training and evaluation phase. And in this part, we evaluate whether this prediction is accurate or not. And here comes the predictive model, and this model decide from the result outcome of the feature extraction. This model decide either this query is similar or dissimilar. So we treat them differently. If it's similar, then we give a recommended plan. So how the query will be executed. Of course, the smaller one will be executed first, and then the larger ones. And this one will update the query execution time prediction again. And if those query are not similar, then we have this data stored and create a new plan by the optimizer. And of course, execute the new query and go back to the original training set. And this whole part are part of the offline training set. And this part is the online and testing set, which will test our trained algorithm to test if the trained algorithm is well enough to optimize the queries. So due to the limitation of time, today we will focus on this part, the feature extraction, because this is also the most interesting part to distinguish the queries, to judge if two queries are similar or not. So this is also our problem today. Sorry. Okay, the feature extraction. There are in total 3 techniques to extract the features from queries. First one is called SparkQL algebra, features with a special temporal extension. And second one is called special temporal graph patterns features. And the third one is query cardinality features. We will come to this one by one. Okay. First of all, the SparkQL algebra features with spatial temporal extension. This one is more about the counters of all the terms appearance in the query. So we count how many times, for example, term is appear in the query. If 2 queries have the same appearance, then we consider that those 2 queries are similar. As an example, this is a query. This is a query, and we count these terms, these keywords, and then give a vector. For example, they have some triple and BGPs, and if the other query have the same amount of the terms like this, then we can consider these two queries are similar. Well, in this case, there's a shortcoming for this approach because this only count the number of the number of terms is doing, but that doesn't consider that what kind of structure it is. So it can be that the two queries with exactly the same terms, but they have a completely different structure. So their execution time could be really different. So that where our second technique comes. This is called spatial temporal graph pattern features, which we convert our query into a graph and compare two graphs, whether the two graphs are similar by using a distance. So this is an example of how the queries are transferred into a graph. There are arrows here, so these arrows can represent the structure of this query. So this gives a much improvement for the features extraction. The last but not least is the query catenary features. This one, just like the normal catenary predictions, as you may consider that the different catenary amount may give a different result in two exactly the same queries. For example, if we want to select 10 samples out of 100, compared to we select 10 samples out of from 1 million, it could of course run in very different amount of time. For simplicity, this approach is just take the spatial operators and semantic patterns into account. So they just give two parameters, then it can represent this feature. Okay. So next comes to the evaluation phase. Here is our evaluation metrics. This formula is meaning that n is the number of samples, and this symbol is that the prediction number of the query, and the other one is the real number. So if they are equal to each other, then we count 1, and we calculate the average of this number. Is our accuracy, and we by using this accuracy, we can calculate the RMSE, which is the root mean square equation, and R square for evaluation. And they did some experiment. So for first one is only using the first techniques we introduced, called algebra features. And as you can see, the result is already pretty impressive. It's around 80%. And this is accuracy after using the algebra and the graph patterns. So by using both of the techniques, we get not that significantly, but some improvement. As you can see for RF, by the way, this RF thingy is algorithm of experiment. We are not going to go detail to this kind of algorithm. It's just calculate how far that the real number is from the prediction number. And as you can see, there are some quite some improvement here. Okay. So these two tables shows that the different of RMSE and R square by using only algebra features and both algebra and graph pattern features. Comparing these two, although most of them are the same, but we can see the running one of those algorithms called SVR poll. The improvements are quite high. So this RMSE number is just the distance that the prediction number from the real number. So this one, the smaller this number is, the better the result is. So this comes from 366 to 130. So it's quite a big improvement on this algorithm. And the paper we are using is it's called the Learning Approach for Query Planning on Spatial Temporal IoT Data. This is published in Proceeding of the 8th International Conference on the Internet of Things. And the authors are listed here, and they from National University of Ireland. Okay, that's